yesterday we ended up in this part where we were trying to look specifically at systems that can be described by linear constant coefficient difference equations, okay? So using the convolution property, we hope to be able to obtain the frequency response of a system like this more easily. So the key idea here is to, suppose you're given this difference equation describing the input-output relation of the system. You can obtain the frequency response by first taking the Fourier transform on both sides, and this will give you a formula like this, right? So for every y of n minus k, you have a Fourier transform that is equal to y times e to the minus j k omega, depending on how much is this time shift, okay? And then dividing x to the left-hand side and moving this summation to the right-hand side, you get this ratio, which is our frequency response, okay? So yesterday we looked at a couple of examples. The first one is simple with yn minus a, yn minus 1 equal to x. So you can follow the same procedure, take derivative on both sides, reorganizing the terms to get this frequency response, okay? Then we look at a slightly more complicated case where you get a frequency response that looks like this. Now, in order to facilitate the computation of the impulse response, right, we like to use the partial fraction expansion to split this into two terms, right? And with the frequency response taking on this form, we know immediately that its time domain impulse response looks something like this, right? Which is basically a decaying geometric series, okay? Right, so we have one last example. So this last example is to pass a signal equal to this, right? So this is, again, a decreasing geometric series with factor 1/4. So suppose you pass this through the system described in the previous example, okay? So you pass this xn through a system that is described by this frequency response here, okay? So again, we want to utilize the convolution properties. So the first step is to find the frequency, the Fourier transform of this signal. Okay, so this is in a form that we are very familiar with, right? So we know immediately that the transform is just 1 over, so 1 over 1 minus 1/4 e to the minus j omega. Okay. So by the convolution property, we know that the output response, the output spectrum is equal to the frequency response times the input spectrum. Okay. So this h we computed on the previous slide. So this h is, there are several forms of this, but let's take this form here, which has in the denominator 1 minus 1/2 exponential times 1 minus 1/4 exponential. And you can see that this factor here is the same as this factor here. So when you multiply the two, you will get a square in that term. So this becomes 2 over 1 minus 1/2 e to the minus j omega and 1 minus 1/4 e to the minus j omega squared. Okay? Okay. So the reason we look at this example is, just to mention the specific detail where when you perform the partial fraction expansion over a term that has a square, that has a higher order term in the denominator, you actually need to split this into two terms, one with the first order and one with the second order, okay? So this is the same as what we did in continuous time. So you split into three terms, let's call it B11 over 1 minus 1 over 4 e to the minus j omega plus B maybe let's just call this B1, B2 square plus B3 1 minus 1 half e to the minus j omega. Okay? So just remember that when you have a quadratic term in a denominator, you need to split into two terms, one of the first order and the other of the second order. Okay? And then you can just combine them back and equate the numerator with this 2, and you will get the coefficients. Okay, so you can find that B1 is minus 4, B2 is minus 2, and B3 is 8. Okay? So then if you just plug them back in, right, plug them back in, and then you can observe the inverse response, inverse Fourier transform. So the first term gives you minus 4, 1 over 4 to the power n, right, times the unit step function. The second term, right, if you recall from the previous example, that this square can be expressed in terms of the derivative of the first order term, okay? So this will give you minus 2 n plus 1, 1 over 4 n un, okay? And this, see example 5.13, okay? So we derived the transform of this in example 5.13. And the last one is the same as the first term, which gives you 8 times 1 half to the power n u times step function n. Okay? All right, so any questions about this part? So for almost all of the examples that we did in this chapter, we had a corresponding example in the continuous time case, right? So if there's anything unclear, you may want to compare with the corresponding example in the continuous time case, and maybe you'll get more insights that way. Okay, so that's all for chapter 5. Right now, after covering chapters 3, 4, and 5, you have actually learned the essence of this course, right? The main part of this course is to learn how to analyze signals and systems, not only in the time domain, but also in the frequency domain, okay? So in chapter 3, we focused on periodic signals and showed that periodic signals can be written as a linear combination of these, finite number of these complex exponentials, basically pure frequency components, okay? Then by extending the period to infinity, right, we get in chapters 4 and 5 the analysis for aperiodic signals, right, and in which case we get the Fourier transform for continuous time and discrete time signals, okay? So the main purpose of these chapters is to learn how to represent time domain signals in the frequency domain, right? Seeing what components of the frequency is contained in the time domain signal. Okay. Right, so this is the essence of this course, right? So in chapter 6, we just elaborate on this relationship a little bit more, okay? So we talk about the time and frequency characterization of both signals and systems and the trade-offs that we may see among the two, okay? All right, so when we look at the spectrum of a signal, we're often accustomed to looking separately at the magnitude and the phase, okay? So suppose that you have a spectrum, capital X of j omega, right? This is the Fourier transform of a particular signal x of t. Then you can write it in terms of a magnitude, right? The absolute value of x gives you the magnitude times e to the j of the phase of this signal, okay? Now you can do this both for continuous time or discrete time Fourier transform, all right? Now the magnitude here tells you, how large is the component of the frequency at this omega, okay? So the magnitude here tells you, how large is this frequency component, e to the j omega, contained inside the signal x of t, okay? So again, Fourier transform tells us that, for a signal x of t, okay, we know what are the frequency components contained in this signal, okay? And the for certain frequency components, they may have a smaller contribution, but for other frequency components, they may have a larger contribution, okay? And the magnitude basically tells you, how much contribution is contained in each different frequency component, okay? Now, other than the magnitude, okay, so this is the magnitude. Other than the magnitude, the phase is also very important, okay? So the phase provides information about the relative phase of the exponentials that are affecting the nature of x of t, okay? Now, if you think about it, what is the phase, okay? So suppose that you have a complex exponential like this, okay? So by Euler's relation, this is cosine omega t plus j sine omega t. All right? So this complex exponential is basically a sinusoid, okay? And the phase tells you, right, at what portion of this sinusoid are you observing, okay, at time t. So this phase, right, for this sinusoid here, you have a phase that increases with respect to time t at a rate of omega, okay? So if you plot this out, you may get something like this. Okay, so suppose that this is cosine omega t, and certainly you can plot something for sine, okay? Now, what is a phase shift? Okay. So suppose that now you shift the sinusoid by phi, okay? So suppose that you, instead of cosine omega t, you get cosine omega t minus phi. Okay, suppose you have a phase shift of minus phi. So what does this mean? This means that at the origin, you're looking at the signal. The value of the signal is cosine minus phi, okay? So this means that the original peak now occurs a little bit later. right, resulting in something like this. Okay, so this phase shift sort of shifts the signal either to the left or to the right, depending on whether this is positive or negative. Okay. Now, when you have signals, when you're okay. Okay, so you can actually also view this as cosine omega t minus omega t naught, where t naught is phi divided by omega. Okay, so suppose you substitute this inside, then you again have this phi, right? So if you write it like this, then you're basically saying that this sinusoid is this sinusoid delayed by t naught, okay? So the peak originally occurring at time 0 now occurs at t naught, okay? So this is why a time shift, a shift in time, right, if you recall, a shift in time has a Fourier transform that is equal to the original spectrum times e to the minus j omega t naught. Okay? So a time shift causes an additional phase shift of omega t naught. Okay. Now, if you have a signal of different frequency, okay, suppose you have a signal of a higher frequency. Right. So suppose you have something like this. Okay. So this is of higher frequency than this, right? And suppose you delay this signal by the same amount t naught. So t naught is here. So you move this peak now to this point. Okay? Okay. So what this does is that now, everything is shifted. Everything is shifted by t naught. Okay? So you get something like this. Okay? All right. Now the yellow curve is cosine. Suppose cosine omega 2t. Okay. Suppose this is the yellow curve here. Then when you delay by t naught, okay. When you delay by t naught, the signal you get is cosine omega 2 t minus t naught, which is cosine omega 2t minus omega 2 t naught. Okay, and this is your phase shift. All right? So even though these two signals have the same delay, the resulting phase shift is different. right? So even though I have a same delay of t naught, because this signal varies at a lower frequency, therefore the phase shift that I see from here to here is actually, this phi value is actually much smaller compared to this signal, which varies from here to here. Okay? So you have a larger phase shift due to the same delay if you have a higher frequency component, if you're looking at a higher frequency component. Okay. Right, and this is also exhibited in this formula here, okay? So when you delay the signal by t naught, this means that the original x of t has many, many different frequency components. But when you delay by t naught, you're delaying all of their frequency components together by t naught. So every different frequency component delayed by t naught experiences a different phase, okay? Experiences a different phase shift that is linear to the frequency omega, okay? Now, if they do not all shift, if they do not have a phase shift that is, linear to omega, then what would happen? Okay? So if you have two frequency components, let's say omega 1 and omega 2, right, that do not have, a corresponding phase shift that is equal to omega 1 t naught and omega 2 t naught, then this means that these two frequency components are delayed differently in time. So when they are delayed differently in time, they do not add together the same way as they did originally. Okay? So it's very hard to draw, but all right, so suppose that originally you had, these two sinusoids that you're adding together, okay? But suppose that they are now delayed by a different amount, okay? So suppose that instead of adding this with this, you're adding this with a slightly shifted version of this. Okay? So you can sort of imagine that when you add together the two white sinusoids, you would get a different signal than when adding together these two orange curves. Okay? So this is why the phase information, okay, this is why the phase information is also very important, okay? Because if you change the phase information, you're basically changing, how these two sinusoids align with each other. And when they are aligned differently, you can get completely different signals.